Cross product. Oh, I'm on the wrong slide here. There we go. The next type of vector multiplication we're going to learn is the cross product. And whereas the scalar product gives us an answer that's a scalar, the cross product gives us an answer that's a vector. But it's not called the vector product. It would be kind of make sense. The one scalar product, one vector product. No. The cross product. So what do? Well, we can use this formula. U cross V is the length of U times the length of V times sine of theta of the angle in between multiplied by a unit vector in the direction that is perpendicular to the plane that both U and V are in. Okay? So if I have two dimensions, and my vectors are here on the desk, then the cross product will produce a vector that's either pointing straight up or pointing straight down. In 3 dimensions, if I put my arms out like this, then it's either pointing that way, oh, I can't do that one, or the other way. So the vectors are joined tail to tail, so you have an angle in between them, and n is a unit vector that's perpendicular to both of them. Which way is it? Well, in order to figure out which way the vector is pointing, we have something called the right-hand rule. I'll also provide another way to help you visualize this as well. So the right-hand rule works like this, and all the words are there to describe it, but I've got a diagram here. You've got U cross V. So whichever vector is first, you put your hand on that vector. So as I have here, I have my hand pointed on the vector and my thumb is pointed up. You could put your hand on that vector with your thumb pointed down. So the decision you have to make is how you can put your hand on that vector so that your index finger can stay pointed on that vector, but your other fingers can move towards the vector V. In this case, you can see that I can do that this way, but if I turned it this way, the only way I can move these other fingers is down. So I have to have my thumb pointed up and move my fingers this way. So U cross V in this case would have my vector pointed up away from both of those instead of downwards. Okay? The thumb is the direction. The other way that you can think of this, if you have ever done some work, well, probably easier, most of you have brushed your teeth. Cross my fingers, hopeful. And when you brush your teeth, you take the lid off the toothpaste and you put the lid back on the toothpaste. So if you think of the action of unscrewing the lid from your toothpaste, that would be moving the lid in that direction counterclockwise. I don't know if you ever learned lefty-loosey, righty-tighty as a kid growing up when you're trying to put things on, or if you've got a wrench. If I've got a wrench and I move it in this direction from U to V, that would loosen it. And when you loosen something, it comes up and off, the same as the right-hand rule. But if you would go V cross U, that would tighten the screw cap on your toothpaste, meaning the vector would be pointed down. That's the first vector. And then, yeah. So if we do V cross U with this same diagram, which is down, no, that's the U cross V, but here if we do V cross U, you would point it at V first. You'd keep your index finger. The only way I can move my other 3 fingers to U is this way, so then it's pointed down. Your index lines up with the first one, and then your other 3 fingers can only bend in one direction. And again, if I would do V cross U, starting at V going to U, if I think about turning my toothpaste cap in that direction, or tightening a bolt with a wrench, that would tighten it, which would force the lid down, making that a downward motion. So most textbooks will have a right-hand rule, or they'll talk about it that way. I actually find the toothpaste cap or the wrench idea easier to visualize, because you just have to twist it and you're like, oh yeah, that tightens it, so that would be going down. Which is interesting because one of the applications that we're going to do in this unit is how the cross product can be used in physics for torque. And when you're turning something with a wrench, you're applying a force, and when you want to tighten something, that force is actually in the downwards direction. And when you're loosening it, it's in the upwards direction. So, U cross V and V cross U are not the same. They are vectors in the opposite direction. They'll have the same magnitude, but they'll be in the opposite direction. So you could say that U cross V is equal to negative V cross U. Okay? So using our formula, we can do some mathematics. The angle between two vectors on a flat surface is 50 degrees. So we know this is 50 degrees. And the length of U is 10, and the length of V is 20. Find the cross product U cross V and V cross U. So if we start with U cross V, it's the length of U, which is 10, times the length of V, which is 20, times sine of 50 degrees times the unit vector n. And so if we multiply these values together, 10 times 20 times sine of 50, we get 153.2 unit vector n. And we introduce the unit vector n where n is a unit vector. And in this case, with U cross V, if you think about going from here to here, that would loosen your cap, so it would be up. If you do the right-hand rule, you can point it here and twist those that way. Right?
If it was V cross C, it would be going down.
It would be going down. Where n is a unit vector pointed upwards.
This X is different than the dot.
This x is different than a dot because this is a vector that we get as an answer, whereas the dot gives us a value. And where you've seen that dot product helps us in finding angles, we're going to see some applications of where the cross product.
Use a dot product to find the angle to find the cross product.
Sometimes. Okay? Yes. I mean, what does it,
I'd say
so on a flat surface,
out of the big.
so the fact that flat would mean like this, then upwards makes sense.
Well, but if you're looking at the screen, there's a flat surface out of the page. In physics, you
Yeah.
can get it wrong instantly.
Okay. So in physics, they would want to say outwards.
Out of the page.
If you say upwards, they'd be like, nope, that doesn't matter.
So what is the difference between upwards and outwards?
Because upwards is like
Out of the page.
outward, like out of the page.
Out of the
Say
page.
Out of the page.
Because if you say upwards, that just means like this is your page, and it just goes like this, upwards, which is
So is this out of the page?
yes.
And if I take the page and turn it, it's still out of the
They
page?
Specify where the plane of the page is.
Yeah.
So it gets complicated, right? I will accept upwards or outwards.
So what if you were meaning like north upwards and not out of the page?
What do you mean? It's upwards.
Yeah.
What's downwards then? It's
If you're okay for a vector.
Yeah.
For a vector which has a magnitude and direction.
Mhm.
Would you say north for if it goes up? Like
Well,
parallel to the
it's upwards from the page. So
So then that wouldn't be up.
But the page wouldn't be on the flat, like you're turning the surface now up and down.
It's always been up and down when you
Yes.
look at it in the screen.
Yeah. Randy, yes.
So V times U would be the same value, just pointing down.
Yes, so V times U would also equal 153.2. And I guess we could write it, since we've already shown n and defined n to be upwards, we could write a negative in front of it. Or if this had been the only question, you could have written it as a positive value and defined n to be downwards, outwards, inwards, anywards. So application number 1 of the cross product. Recall the area of the parallelogram. Do you remember what the area of a parallelogram is?
Average of the top and bottom.
Average of the top and the bottom times the height. Okay?
Or the average of the sides, that'd be the height.
Now, since the top and the bottom are the same length, it's basically just base times height, right? You could take the average of the top and the bottom, but since they're the same length, the average is just the bottom.
Wait, is that a parallelogram just always has the top and bottom be the same size?
And the sides as well, right?
Just like a
Otherwise, it would be a trapezoid.
so slanted rectangle.
Yeah, like when you sit on a cardboard box. Okay? So here I've got a diagram shown. Well, I think I've got it on the next screen too. There's our diagram of a parallelogram. And so we would need base times height. Now, if we add the angle theta in here, we could define sine of theta to be opposite over the hypotenuse, which is your height over the length of the vector v. Rearranging that for height, we get our height to be just the vector v times sine theta. And if we substitute this into our formula for base times height, we can now replace the height with v times sine theta, and we know that our base was the length of the vector u, and so our area of a parallelogram is just the length of the vector u times the length of the vector v times sine theta, which you might notice is just the beginning of the cross product without the unit vector. In other words, it's the length of the cross product.
Are all the angles in the parallelogram the same?
No, as you can see from here, this angle and this angle would be the same. These two angles would be the same.
So then,
And the black angle plus the green angle would be supplementary or add to 180 degrees.
so if you're given the green angle, you have to solve for the black one.
If you're given the green angle, you could solve for the black one. But if you have two vectors, tail to tail, this will work even if you get the obtuse one. Right? Because if you're given the obtuse one, here, let's do, right? Then this angle here, when you solve for it, will give you the same value for sine theta as this angle, right? Because you have quadrant 1 and quadrant 2, and they would have the same reference angle. And then you would still calculate this height based on that angle. So this formula will work whether you're given the obtuse angle or the acute angle between them. No, you could use either one. So this is just the magnitude of the cross product, and so our new area of our parallelogram formula is just the length of u cross v.
The crossing formula includes that.
So the crossing formula would include the n, right? But once we do the magnitude here, it would just become the length of u times the length of v times sine of theta. Where's the sine of theta? It's in here, right? If we look at what, if we look at the very beginning, right? U cross V has the sign of theta in it. And as soon as we take the magnitude of this, we will just get this first part because the magnitude of a unit vector is just 1. So if we look at example 1, where we had u and v and the angle between them being 50 degrees, and we knew that the length of u was 10 and the length of v was 20, we can now find the area of this parallelogram. And what's the area? 153.2, whatever the units were. Newtons. We don't need the unit vector because we're finding the length of the cross product. Okay? Which we just showed how it's related to the area.
Well, I see, no, but like, I see how it's mathematically, like,
Yeah. Right. But conceptualizing, you're imagining a vector pointing straight up, and you're like, oh, that's the area of this thing down there, is kind of just a nice coincidence or application. The Cartesian form of the cross product. So if you didn't want or you didn't have a calculator, right, because with the calculator you need to find the angle between them. And let's just say you had two vectors and you wanted to find the cross product and you weren't allowed to use your calculator, is there a way just to use the components to find that? Just like the dot product, you could use a protractor to measure the angle. A little bit hard in 3 dimensions. Say, can you hold this right here as I measure out this angle in 3 dimensions? Now, here's our formula. We're going to go A2B3 minus A3B2, A3B1 minus A1B3, and A1B2 minus A2B1. Maybe this reminds you a little bit of matrices. A little bit too much. Remember when we were doing determinants and we were doing like 3 by 3s? So, well, yeah, because you could rewrite the first 2 columns, right, and drew the arrows?
I didn't do that one.
You didn't do that one?
I just had the formula memorized.
You had the formula memorized, or you
No,
took
for
the...
the 3 by 3.
Okay. For the 2 by 2 you did.
Yeah.
You just did a cross and a cross, or you just did the formula.
A minus B terminated part.
Okay.
No, wait. No, hold on a minute. That was the 3 by 3. No.
The 3 by 3 matrix,
You just eliminated the rows?
the 3 by 3 matrix, 1, 2, 3, 4, 5, 6, 7, 8.
Yeah, and then you
So you eliminated these ones and then these,
yeah.
and then you eliminated those and did those, and eliminated the next and did the next ones.
Like, hold on. Let me
Thinking the inverse or something.
wait, I'm already here.
No, he's thinking of the determinant.
Okay.
No, because there was A, your something minus B something
Yeah.
plus
See something.
So you have like a 3 by 3.
Yeah. Good. So you remember that formula from matrices. This is going to be connected to that. Okay? For those of you that rewrote things, you're going to like this. So what you do is you rewrite vector A, I'll call it, twice. You rewrite vector B twice. And you write ijk twice. Draw your arrows this way. Those ones will be positive. Draw your arrows backwards. Those ones will be negative. Combine the like terms, because some of them will be with vector I, some will be with vector j, and some will be with vector k. And as I was doing this, I thought, oh, I think I came up with an even better way that's kind of connected to the matrices. And it's something like that. Okay? But I'll show you with numbers, because with letters things get a little bit confusing. So, method number 1, which is the IJK method. You take your first vector u, 2, -1, 5, 2, -1, 5. You take your vector v, -6, 3, 8, -6, 3, 8. Where do you draw your arrows? Starting from the j. -30j, 6k, -8i. Here's our negative ones, starting with the k, which will be 6k and negative. 15i and negative. 16j and negative. Okay? Put things together. We've got -8i minus 15i will give us -3, 23. For our j, -30 minus 16, -46. And for our k, 0. There is our vector that is perpendicular to both the other vectors. What's that? Then this is, yes, so this is u cross v equals this.
So if you wrote v on top, it equals an answer?
Yes. Well, it would be the negative of that. It would be 23, 46, 0. Yes.
Is it always the column vector going to be I, J, K?
Yes. Column vectors I, J, K always.
What's your arrow for red eye?
Which I arrow are you?
Red. No? There's no arrow. There's an arrow on every single one.
I'm so lost on arrows. This arrow?
Oh,
This arrow?
It's like when you like multiply the 15i. The 15i when you multiply.
I flash 3.
The cross.
Oh, he's talking about the
The
red line.
actual
You only have
board.
2 red lines.
Oh, I missed the red line. There we go. Okay. Whew.
I was so confused.
Okay. So I found, this works. Some things I don't like about this is, where do you start your blue arrow? Why don't I start it should I start it on I? I mean, I guess it would work out to be the same if you started it on I instead of starting on J, but it just,
J, that means if you start J both sides.
you could do that. Okay? Now, so what I did is I looked at, is there another way that might even be easier to do this? So here is u and here is v, and I want to do the cross product between them. U was 2, -1, 5. And v is -6, 3, 8. And just like the determinant of a matrix, when I want to find the first row, okay, I'm going to take dark highlighter. I'm going to ignore that, okay? And because it's a cross product, do this. -8 minus 15, -23. This is nice. You liking this? Okay. So we've got, and it fits with all of the determinant stuff that we did, right? Because this one is positive and this one is negative. Okay? So let's do that again. I should just delete those things. I could erase them. That would work too. Next row, move this down. Cross product again. Okay? And watch what happens here. Just like in the determinant, when you did the second one, the first one was positive, the second one was negative, and then it went positive, negative, positive. So watch this one. When I do 16 plus 30, right, minus a negative 30 actually, right, I get positive 46. But the second one, whatever answer you get, you make negative. Just like in your determinants, it's positive, negative, positive.
So whatever you catch, so if it's a negative 46, you switch it to positive.
That's right. Okay? That's only for the middle one. And then when you get to your third one again, okay, this one can be positive this way, 6, minus 6, 0. I like that. Okay? But you'll find that, I don't know, I just sort of made that connection between our matrices and this. I like it because it has that cross idea in its product. And it does, the part that you have to remember is that it goes positive, negative, positive. But you can use the same thing every time. And that works out to the same as this idea, but it's less complicated to set up. And the mental math, you can do it without any drawing anything. You can just sort of write it out and write the answer. I guess a negative of this method is you're not really showing any work. So when you make mistakes, mental math errors, there's not really any way to show what you did.
What if this is like 4 more questions out of homework?
If you do it, I would take off a half mark, right, Ramsey? So let's just get that.
Bell rings in like 20 seconds.
20 seconds at 2:36?
Is it 2:36?
That's the longest 30 seconds you're going to experience in quite some time. So the cross product is that. So if we can imagine U cross V 7, 3, 1. Because they were written that way and they say the cross product. So we just assume.
Let's quickly go give someone a starter. In like 10 seconds.
In 10 seconds, so in 3 minutes?
Yes.
Okay. So I would probably do the same thing we did last time. I would say, okay, I'll take that out. 3x minus 4 has to equal 2. X is equal to 2. Okay. Let's do a check if I move it down to here. 3x minus 4 has to equal 2. If I move it down to this, whoa.
Can you do it like in steps?
Yeah.
Like you get your vector.
So
x minus 4.
I went from here and I went this one, 3x minus 4 is the number that I would put there.
Yeah, like I put it there. Just for this, but then can I do it differently after? Like I get my,
Oh, you did the cross product with the x?
with the x's in there, so my first is 3x minus 4.
Right.
And then after, just equate.
And then just equate the two. That would work as well. Yeah. So what Riley is saying he's doing is he's making his vector that's the answer with the x's. This one will be 3x minus 4. If he moves this down to here, If he moves that one down to there, this one will be negative 7x minus 3. And then the last one should be 28 minus 9, which is 19, which matches up already. So if we use the first one, 3x minus 4 has to equal 2, well, then we get x equals 2. Now we should check to make sure that that value holds. 14 minus 3 is 11 times the negative, negative 11. Yes, it works. What's that? Well, it could be that they give you the wrong value here, right? Like if it could be a mistake. Like I could write the same question. Consider the vectors blah, 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 and blah, blah. The cross product is 2, negative 10, 19. And then it would have been a mistake because it doesn't match. The x doesn't work for both the 2 and the negative 10. There's just an error in the question. Then on a test or a quiz, if I make an error like that, I'd give everybody 100% on that question because it's an error.
But what does that tell you about that x value? The one
In this case, it's 2. X is 2. If I'd had it as 10, there is no value of x that works.
Is there questions designed to be like that, where you have to actually figure out if it works or not? Like, is that part of the question?
No. In a case like this, if they're telling you find the value of x, there's going to be one value of x, and that's going to work.
But if it was negative 10, you'd just be like, there's no
There's no solution to this.
Could it be like on the matrices test where there's 2 edges of x, but only one of them works for everything?
It could be, but then there would have to be an x squared in one place, something like that. Then you would have to check. Find the area of the parallelogram. Oh, this is where we'll have to end.
That was 37.